All right, good morning, everyone. I'm going to go ahead and get started with the lab today on diagnostics. Just a couple of things before we get started. So I'll be presenting everything in R today, and we'll be walking through conceptually with the programming how to run diagnostics on an example data set. For SAS and SPSS users, I'll be posting materials after lab. There's a detailed handout for each program, as well as syntax. So they're not templates as the labs have been. It's full syntax that you could just keep on hand in case you have to run diagnostics. And all the code that you need will be in those files for both SPSS and SAS. All right, so I'm gonna go ahead and share my screen here. If anyone has any questions, let me see if I can pull up the chat somewhere. I don't know where it is. Yeah, just go ahead and speak up if you have any questions. I don't think there are too many of us here right now. So if you have any questions, just go ahead and throw it into the, throw it in. All right. Can everyone see my screen? Okay, cool. So this is a diagnostics example. The materials are taken from a class that I took with Leona Aiken. It was probably the last time I think she taught this regression class. She's an author of a book called Applied Multiple Regression and Correlation Analysis for the Behavioral Sciences. And so the data set that we'll be working with is taken from a textbook by Tabachnik and Fidel in their book called Using Multivariate Statistics. So I'll be posting this data set later on Canvas. The file name is example6data.txt, and we'll see that in just a second. And then we're dealing with 4 variables here. So I'm going to go ahead and read in the data before we talk about the variables. So this syntax here was created by Brian Keller. He's a former student here at ASU. And I made a couple changes here, but it's all pretty much his code. So I'm going to start by loading these packages here. You'll need the car package and the site package. All right. And then to read in the data set, I'm going to create an object here called mydata.orig for original. And the data set is actually, it's a text file, and it's in fixed width format. So let me show you what that looks like. All right. So this is what the data look like. There are no variable names, and then we have, you can kind of see that it's organized into these 5 different columns here. So that's what we're going to read in. And so the way that this code works is it's saying that each width of each variable is 4 spaces. And that's why we have 5 4s here. So the first variable is 4 spaces wide. So if we click into the actual data set, 1, 2, 3, 4. So that's the first variable. And then the second variable is also 4 spaces, 1, 2, 3, 4. Third variable, 1, 2, 3, 4. And then the same thing for the last 2 variables here. So that's essentially what we're telling R in this width statement here. All right, so we're going to use the read.fixed width format function here. Just like with all the other labs, I placed the data set on my C drive in the datasets folder, and then this is the file name here, exnp6dat.txt. And remember, all the dataset location and file names are wrapped in quotes. And then we have this width statement. And then here I'm adding column names. So I'm adding variable names. So we have subject number, time doctors, physical health, mental health, and stress. There is no header, so that's false. And if you want, you could always type it out. And then we don't want to skip any blank lines, so that is also false. Okay, so we'll go ahead and read in the data. Then if I click on the object here in my environment tab, you can take a look at what we have. All right, so subject number, pretty straightforward. Time doctors is the number of visits to health professionals. Physical health is a measure of physical health. And then we have mental health. And then we have a measure of stress. And as scores increase, that indicates more of physical health or more of mental health or more stress. Actually, so the higher scores mean more physical health problems, and then higher scores on mental health mean more mental health problems. And then stress, obviously, those are higher levels of stress.
So which one is the dependent variable?
The dependent variable is going to be time doctors.
Okay,
so
got it.
Number of visits to health professionals. All right. And then what I'm going to do here is I'm going to subset my data set. So I'm going to create this new object called my data. And I'm going to use the subset function, and I'm going to choose. So from my original data set here, I'm going to choose everything that's greater than or equal to 51, as well as anything that's less than or equal to 78. And that's for the subject number. So essentially, I'm selecting out subjects 51 through 78. So I'll go ahead and run that, and then we can look at what that new data set looks like. So we have 22 observations, and then we have the same 5 variables. So as you can see, we have subject 51 all the way to 78. And the reason why we're subsetting the data is just so it's a little bit easier to go through diagnostics. If we're doing it with all 466 observations, it's a little bit more difficult and a little bit messier. So any questions so far, as we're, it's just data manipulation right now, so no diagnostics yet. All right. And then here, I'm gonna rename the rows. So if we look at my data, the row numbers are just random. They're kind of from the subset of the rows. So these were the original row numbers, 43, 44, 45, and it doesn't really match up with the subject number. So I want to change that, and I want to change my row names for my data set to the subject number. And remember, when we refer to variables from a data set, we specify the data set first, so my data, and then the $ to indicate that we're going to pull a variable, and the variable that we want is subject number. So when I run that, when we take a look at my data, you can see now that the row numbers match the subject numbers. All right, so that was a lot of data manipulation. So let's go ahead and start looking at our descriptive statistics. So in the psych package, I'm going to use the describe function on this subset, so my data. And again, you just want to take a look at minimum and maximum values. As you can see here, the minimum here is 13 and the maximum is 920. So there might be an issue there for the stress variable. 0 to 18 looks okay, 2 to 10 looks okay, 0 to 20 seems reasonable. And then these are just subject numbers, so we don't care about this first row here. Also, if we're looking at skew and kurtosis, everything looks to be pretty reasonable, close to 0. So for time doctors, everything is pretty close to 0. Physical health, everything pretty close to 0. Mental health, everything close to 0. But then when we get to stress, it seems to be a bit more skewed relatively compared to the other variables, as well as a little bit more kurtotic. So we'll want to keep that in mind as we move forward with our diagnostics. All right, so let's go ahead and plot stress and take a look at and see what its shape looks like. So I'm going to create this object here called histo, and I'm going to use the hist function to create a histogram of my stress variable here, and then I'm going to give it a title, So main equals, and then in quotes, the title will be histogram of stress with normal curve. So here's our initial histogram. And it does indeed appear to be positively skewed. And we can see that while everything is pretty much between 0 and 600, we have this one observation here, which is the value of 920. So there seems to be a pretty big gap here between the cluster of scores over here and then this one outlier out here. So what I'm going to do now is I'm going to superimpose a normal curve on here to kind of give us a frame of reference. So you don't have to understand this code at all. I would just run it, this chunk here, but I will go through what everything is doing. But if it doesn't make any sense or you don't care, it really doesn't matter. So what I'm going to do first is I'm going to create 40 points that are equally spaced from minimum stress to maximum stress. So I want to take this, my values on the x-axis here from 0 to whatever this maximum value is. And I want to create 40 equally spaced points on x. So I'm going to name that xfit, and I'm going to create a sequence from the minimum of stress to the maximum of stress. And I want it to be, I want the length to be 40. So I want 40 points. So I'll run that first. And then now I'm going to evaluate each one of these points from xfit. I'm going to evaluate them on a normal distribution. So essentially, I'm trying to figure out, now that I have 40 points from the minimum of stress to the maximum of stress, I want to figure out at each point, what's the height of the normal distribution. So that way I can plot that curve here. So I use a function called dnorm. It'll give me the density of the normal at each value of xfit. And I'm going to, and then the mean is going to be the mean of stress, because that's the variable that we care about. And then the standard deviation will be the standard deviation of the stress variable as well. Go ahead and run that. And then the last thing that we'll do here is we'll rescale y to fit, to match the histogram axis. So you do that with this bit of code here. We're taking the original y fit, and then we're multiplying it by the difference here of the histogram midpoints. So I'll go ahead and run this line. And then finally, we could just plot our normal curve here. So as you can see, we have this bar here that kind of exceeds where the normal curve is. So it does seem to be positively skewed when we compare it to a normal distribution. All right, any questions so far? Okay. So now I'm going to plot the same histogram, but I'm going to increase the number of breaks. And this will allow us to better visualize that gap between that outlier and the rest of the points. So I'm going to create an object called histo2, use the same hist function, and I want to plot stress, but I'm going to specify that the breaks are equal to 10. And the breaks are related to how many histogram bars that we have. So I want the breaks to equal 10, which is more than the default. And then here again, we're just specifying a title. So if I plot this histogram, it looks a little different. So now we can clearly see that there's the gap between this outlier and the rest of the points is pretty large. And then I'm going to run this bit of code again. It's the same thing that we did earlier to superimpose a normal curve on top of our histogram. As we can see again, our histogram bars don't really match the shape of the normal curve here. So we could be pretty confident that there's some positive skew going on here, mostly because of this outlier here. All right, and then another thing that we can use is a box plot. So again, we're just going over different visualizations of our stress variable because that's the one from our descriptives that looks like will be problematic. So we'll plot this box plot here of the stress variable again, and then here again a title. So when I run this, remember that the box plot, we have the minimum here, the minimum value of stress, the maximum value up here. We have the first quartile, which is this end of the box. We have the second quartile, which is the median, that's here. And then we have the third quartile. And so it's kind of like taking a normal distribution and then flipping it on its side. So we want to make sure that these are kind of equally spaced from the box here, and then that the median is in the middle of the third and first quartile. And that gives us an idea that this here is normally distributed. But the thing that we're missing is out here we have an outlier. And so this is what's skewing our distribution. And so this box plot it makes it pretty clear that we do have this one point here that is not with the other points. All right. And then now we can take a look at our correlations, which is something that's good to do before running our regression analysis. So essentially what we just did right now was a bunch of visual inspection. We just wanted to look at plots so that we could visually inspect that variable that the descriptives told us would probably be an issue. And it does look like it's an issue, so we're going to go ahead and run our regression analysis so we can compute some diagnostic measures. So I'll start with the correlation matrix here with the core function. And then what this bit of code is doing here is, so in my data set, I want a subset. And so when you use brackets, whatever's left to the comma is referring to the rows. And when you leave it blank, that means that you want all of the rows. On the right here, to the right of the comma are the columns. And so if you leave this blank, it means that you want all of the columns. But if you specify a number, it means that you want to look at those columns in particular. But here we have a -1, which means that it's going to drop the first column, which is subject number. So remember that if we go into my data set here, our first column is subject number. And we don't want to compute correlations for subject number. So what we're telling the correlation function here is I want to use my data set, but I want to drop the first column. So just produce a correlation matrix of everything but the first column. I feel like I said that a million times. Okay. So I'll just go ahead and run it. And then you can see here that we get a correlation matrix with everything but subject number. So we have ones on our diagonal here, and then we can see the correlations between the different variables in our data set here. And they all seem to have moderate to high correlations. We'll go ahead and run our regression. So I'm going to create an object called reg1, and then I'm going to use the lm function to estimate my regression model. And so I want to predict time doctors from physical health, mental health, and stress. And the data set that we're using is my data. So I'll go ahead and run that line there, and then I'll request a summary of reg1. Okay, so if we're looking at our coefficients here, physical health is not a significant predictor, mental health is not a significant predictor, and stress. So none of them are significant predictors of time doctors. And then when we look at the overall model, it is significant. So the model as a whole, with all three predictors, contributes significant prediction of time doctors, but the individual coefficients do not. And that is probably because there's a lot of overlap between these predictors, which we saw in our correlation matrix here. So let's see. And then if you want a more in-depth ANOVA table to see the sums of squares, you can use the ANOVA function, and that'll give you all the sums of squares that you need. All right, so we ran our regression model so that we can continue on and compute some case-wise diagnostics. Are there any questions before we get into the diagnostic measures?
I have a question. Why did we take a subset again? I forgot.
So there's 466 observations in the original data set. And so we subsetted just so that we can look at a smaller set of observations. We could look at all 466, but that would take forever. Any other questions? Okay. So in this R code, Brian Keller actually, he put this in here, which I think is really useful. These are all the functions that we're going to use. So residuals, R standard, R student, and then he defines what those are on the right side here, which is really nice. So we can get the raw residual, the studentized residual, the studentized deleted residual, leverage, Mahalanobis distance, DF fit, or DF fits, and DF betas. Okay, so we're going to start with the Mahalanobis distance. And so I'm going to create this object called Mahal, and then I'm going to use the Mahalanobis function. And what I'm going to do here is, from my data set, I only care about the predictors. In terms of Mahalanobis distance, we only want to look at the predictors here. So again, we use these brackets to subset from our complete data set. And so we want all 22 observations. And remember that the observations are the rows. So that's why we leave this space on the left side of the comma blank. But in terms of columns, we only want physical health, mental health, and stress. And so that's why we put those here on the right side of the comma, inside of the brackets. And then we're going to center the values at the means of the variables. So here I'm using the column means function. So if you look at the data set, each column is one variable. So when you compute the column means, you're computing the mean of each variable. So I'm going to take the column means of my predictors, and that's what I will center the Mahalanobis distances at. And then for the covariance matrix, again, it's the same thing. I just want the covariance matrix of the predictors, not the criterion. So I'll go ahead and run this, and then that'll create the Mahal object, which will be our Mahalanobis distances. And then now I'm going to create another object called case diag for diagnostics. And I'm going to create a data frame that includes all of these diagnostics here. So we had to do the Mahalanobis distances separately because because the function is large. So it's always good to break it up if you have functions that require a large number of statements. So we created this separately, and then now we're going to create a data frame that contains that object. So we're including it here, as well as adding all of these other diagnostics. And remember, so diagnostics, they break up into, we have a distance, we have leverage, and then we have influence. The ones that we'll be focusing on the most for this example will be influence. We want to see how the regression coefficients change as cases are removed. And in the lecture, there are cutoff values for each of these different diagnostics. But for this example, I'm just going to be focusing on whichever one is whichever case number is the worst. And I'll show you how we look at that in just a second. All right, so I'm going to create this data frame that has all of our diagnostics in it. And then here, I'm going to order all of the cases. This negative means that I want it in descending order, so from greatest to least. And I want the absolute value. I want the absolute value of each of the different diagnostics. And so if we run this chunk here, now when you use the order function, it will give you the row number. So here, 13 is the worst for most of these. So we have 13, and then here we have 8, that's the worst for leverage and Mulholland-Nobis distance. And then 17 seems to be the worst here for stress, or for the SD beta for stress. Okay, so keep that in mind, row 13, row 8, and then row 17. So if we go back into our data set, row 13 is 1, 2, 3. So that's this, that's case 69 here. Hold on a second. That's not right. Oh yeah, that is right. Okay, so case 69 here, this is row 13. That's the one that's coming up first in a lot of these when we order them. And then case 8 is 59, which is that outlier that we have. That's 920. And then 17, so 13, 14, 15, 16, 17, that's this one right here. So case 73. So the ones that so 59, 69, and 73. So if we go into our diagnostics, there's this object here, case diagnostics. If we look at 59, this is the row here. And so these are the values. So the values where 59 was the worst were for the residual, the studentized residual, the standardized residual, SD fit, and then 2 of the SD betas for physical health and mental health. And so essentially what we were doing with this ordering function was ordering these different values so that we could see which case number we should be worried about. And again, we want to look at 59, 69, and 72. All right, I know that was a lot. So any questions about what we're doing there? So let me summarize. So we're collecting all of our diagnostics. We're putting it into this object called case diag. And so if we look at what that is, we have our all of our diagnostics by observation here. So for subjects 51 through 78, we have the raw residual. We have these other distance measures. We have the leverage, and then we have the SD betas and SD fits. And so what we want to look at is which ones, which values are the worst, and what corresponding subject does that worst value correspond to. And so that's what this order function does for us. Okay. So I'm going to go ahead and create a scatter plot now. I'm going to plot physical health against time doctors. So physical health is one of the predictors, and then time doctors is our dependent variable. I'm going to add a title here. And then what I want to do is add labels as well. So let me just plot this. So here we have our original scatter plot with physical health plotted against time doctors. And then this line here will add the labels. So for my data, I want to add text. And so I want time doctors from physical health. That's the relationship that I'm looking at. And I want to add some labels here. And I want to use the row names of my data set. And so the row names, remember, are the subject name or the subject numbers. And then position 4 means that I want the labels to be on the right side of the dot. So go ahead and run that. And then you can see here that we get our subject numbers to the right side of each point. And so remember that we're looking at 59, 69, and 72. 59 is here. That doesn't seem to be a problem when we're looking at physical health against time doctors. 72 is right here. That also doesn't look like a problem. But here we can see that 69 is out by itself over here. So when we were looking at our diagnostic measures, it looked like there were 3 cases that we should be worried about. And now it looks like it's getting narrowed down to 1, which is observation 69. Okay, so I'm going to do the same. Let's see. Now what I'm going to do is I'm going to plot the same scatter plot here. I'm going to add a regression line. So we use the AB line function, and then the linear model that we're looking at, or the regression model that we're looking at, is time doctors predicted from physical health. The data set is my data, and I want the line to be red. And then again here, I'm going to add labels, but this time I only want to label 59 and 69. So I'll just run this all together. And if we zoom in here, again, 59 seems to be in line with the rest of the points when it comes to physical health against time doctors. So this doesn't seem to be much of an issue, but 69 still seems to be an issue. Okay, now I'm going to take the second predictor, mental health, and plot that against time doctors. Same line here as above to superimpose a regression line. And then I want to label 59, 69, and 73. All right, so again, 59 looks okay when we're looking at mental health and time doctors. 73 looks okay, but 69 seems to be out here again. So 69 seems to be the one that's problematic. And then finally, we'll look at the relationship between stress and time doctors. So we're going to go ahead and plot stress against time doctors. We'll add our regression line, and then we'll plot, or we'll label those same 3 subjects to see where their points fall in the cluster of points. So here, whenever it decides to load, there we go. So 59, again, not really a problem. 73, not really a problem. But 69 does seem to be a problem. And this was what was mentioned in class. So even though this value here is kind of extreme on stress, it's still in line with the regression here. So it may be an outlier, but it's not influential. Whereas 69 here seems to be influential because it's not in line with the regression line here.
Patrick, out of curiosity, what does the infinity symbol indicate in? Is that like it's just above 73? Is that not an infinity symbol and 2 dots put together, just as I was saying that aloud?
Yeah.
Okay, perfect.
Yeah. No, that's yeah, I didn't even see that, but that does look like an infinity symbol. All right.
Hey, Patrick, in the AB line command, you're running the regression. I noticed you're not running the full regression, but you're just doing it 1 variable at a time.
Yeah, I just want to see stress predict. Yeah, I just want to see the 1 predictor predicting the criterion. I'm not interested in the line from the, so it has to be only one predictor for us to get a line. Once I exceed, once I get into multiple predictors, then we're looking at a plane, and then it goes hypergeometric pretty quickly.
Okay.
So yeah, you're right. We should be considering the effect of the other, or we should be controlling for the effect of the other variables. And I'll show that in just a second, but this is just giving us a rough idea by looking at all of the individual relationships with the criterion.
Got it. Thank you.
Good question. All right, any other questions? So before we move on.
Patrick, I have a question about going back to the ordering. When you said that you're looking at the absolute values of each of the diagnostics, can you say what criteria it was ordering it based on again?
It's greatest to least.
And greatest to least of the absolute values?
Yeah, the absolute values of the these values in here that are in the case diagnostics object that we created with all of the diagnostic values.
Okay, thanks.
Okay. All right, so what I'm going to do next is I'm going to plot the residuals as a function of the predicted scores. So predict reg 1, what that will do is it'll produce the predicted scores, and then residuals of reg 1 will give us the residuals. And then we'll add an X label here and a Y label, and then a title. So here's our initial plot of the predicted values against the residuals. And then we're going to add a regression line where we predict the residuals from the predicted values, and we want the color of that line to be red. And we're using this AB line function again. And then again, we'll label our case numbers that we're concerned about. All right, so this is what we want to see. We want it to be flat. But again, we can see that case 69 here may be a problem. 73 doesn't really seem that bad, and 59 doesn't seem that bad either. All right. So through all of the visual inspection, what you're trying to do is just get a feel for what might be causing problems or what is likely to cause a problem. There isn't, there isn't like a clear-cut criteria when you're looking at a plot, what is out of bounds and what is inbounds. So it's just about gathering evidence for whether or not a certain observation will affect the regression or not. And so right now, with all the plots that we've looked at, it's most likely that 69 will cause a problem. Okay, so touching on Rowan's point, we're going to go ahead and create what are called partial regression plots. They're also called added variable plots. And what these look at are the relationship between two variables controlling for all other variables. And so the function that we're going to be using is AB plot, and this is in the CARS package. And so we want a partial regression plot. And what we're interested in is this model here, reg 1. And that's the model. Hold on one sec. I just want to. So remember that reg 1 is time doctors predicted from all three of our predictors: physical health, mental health, and stress. So it's the full model. All right, here we go. So that's the regression model that I'm interested in, and I want a partial regression plot of physical health. And then here again, we have our observations that we're concerned about. And then this is an option. You can produce a grid, but we don't want a grid. So we just, the F here is for false. And so we can go ahead and plot this first one. And so remember, the what it's plotting it against, all you have to specify here is the predictor that you're interested in. Because we're specifying reg 1, it already knows that the criterion is time doctors. And we'll see that in just a second, because that'll be on the y-axis. Okay, so physical health, this pipe here means controlling for all other predictors. And then time doctors, controlling for all other variables. So physical health against time doctors. And then, let's see. So in this plot, mental health and stress are partialed out of both the predictor, physical health, and time doctors. And case 69, which had high leverage and distance and influence, is lowering the slope. So it's flattening out this line here. So if we were to ignore this, you can kind of see that there's a relationship here where time doctors is increasing as physical health problems is increasing. But because we have observation 69 here, it's flattening out our line. Okay. I'm going to create the same plot for mental health, partialing out for all other variables. Let's see. Just give it a second here to create the plot. Okay, so we have the opposite thing happening here. Case 69 is actually increasing the slope. So if we were to ignore this point, the line would probably be flat. But because we have case 69 here, it's making it look like there's a relationship here between mental health and time doctors. And again, this is mental health partialing out for all other variables or predictors, and then this is time doctors with all the other variables partialed out. All right, and then finally the last one, which is stress. And then here, the same thing is happening as with mental health. So 69 is actually increasing the slope. All right, any questions about the partial regression plots?
So Patrick, just to confirm, so I think, so what you're doing is you're plotting the full regression line, but the scatter plot is basically just the Y and the X, right?
Well, yeah, so the regression line is not the full model. It's the reason why we specified the full model is because we want to partial out for the other variables. So the regression line is between stress and time doctors partialing out for all other variables.
Oh, so this is not the full regression line then?
No.
Oh, okay, I see.
All right. Any other questions? Okay, we're almost at the end here. All right, so what I'll do here is I want to create a histogram of the residuals with a normal curve superimposed. So I'm going to create a new variable. And the way that we do that is we specify the data set that we want to add our new variable to, which is my data, and then a $sign here to indicate that a variable name is going to follow. And then the variable that I want to add is residuals. And what that variable is, it will be the residuals of our model reg1. So I'll go ahead and run that. And then if we look at my data, now we have this new column called residuals. Now I want to create the plot. So I'm going to use the histogram function. I want to plot the residuals. I want 7 breaks, and then here's a title. So here's our initial plot of the residuals. And then just as we have done earlier, I want to superimpose a normal distribution onto this histogram. So this is the same code as we saw before. I'll just go ahead and run it all at once. And then we have our normal here superimposed. And again, the plot of the residuals looks to be positively skewed. Okay, and then the last plot that we're going to look at is a QQ plot. So we're going to use the QQ norm function, and then we want to look at the residuals, at a QQ plot of the residuals. We're going to name the y-axis residuals, and then we add this title here. And then we're going to add what's called a QQ line. Again, it's for the residuals, and then we want the line to be blue. So if I go ahead and just run this. So what we're plotting here are the residuals against some theoretical quantiles, and the theoretical quantiles are based on the normal distribution. And so the way that you read this plot is if everything is clustered around this line here, the QQ line, then we can conclude that the distribution is normal. Or normal enough. If it takes on a different shape, or if it starts to deviate from this this QQ line, then it's indicating that it's not normal. And so here we kind of have like a happy face, right? If you can kind of picture that. So this indicates that it's positively skewed. If it were negatively skewed, it would actually make a sad face. So it'd be bowed this way. I don't think we went over this in class, the QQ plots. Are there any questions about this? It's just another way to visualize the shape of our distribution, which in this case is the distribution of the residuals. And because it's making a happy face, it is positively skewed. All right, finally, the last part here. So we're going to run the regression, omitting subject 69, which is the one that was causing problems according to our diagnostics and all of the many plots that we've created today. So I'm going to create this object called reg1.69omit. And so this with function is essentially taking this LM function, which is our model, and then combining it with this subset function here. So what I'm telling R to do is I want my regression model, which is time doctors predicted from physical health, mental health, and stress. But the data set that I want to use is a subset of my data. And the way that I'm subsetting it is I want to remove case 69. So that's what this exclamation equals means, is that we're removing case 69. So let's go ahead and run that. And then we can get the summary of this regression with 69 omitted. And then the summary of our original regression that includes case 69. And so I'm just going to go ahead and make this larger so we can see it all in one. Okay. So as we can see, case 69 has decreased the slope for time doctors on physical health. So when it's removed, it's the relationship is 0.62, or that's our regression coefficient. But when it is included, the coefficient drops down to 0.01. But as you can see, it doesn't really matter because it's non-significant in both. And then K69 also increased the slope of mental health. So here without K69, it's 0.42. And then it jumps up to 0.71 when K69 is included. Here, there's a little bit more. I mean, this is kind of close to being significant, so it's 0.07. So if this were significant, if it changed to being significant, it would be more of a problem, but it's not. So the conclusion doesn't change here. And then K69 also raises the intercept. So here it's negative 2.42 without K69, and then when we add it, it jumps up to negative 0.68. And then the last thing that we want to note here is that without K69, all of the standard errors here are smaller than when it is included. So let's see. So essentially the only thing that changes, so the results for physical health and mental health predicting time doctors, nothing really changes. The coefficients change, but the conclusions don't change. So that's a good thing. But the conclusion does change for stress. So when we remove K69, stress becomes a significant predictor of time doctors. But when we leave 69 in, then stress is no longer a significant predictor of time doctors. And so that makes it a little bit more tricky because removing the problem observation now makes the predictor significant. And so you can get into issues of p-hacking and whatnot. So that's just something to keep in mind. But as a whole, our model remains significant. So the combination of the three predictors are providing a significant amount of prediction for time doctors. All right, I think that's it. All right, so are there any questions about any of the stuff that we went over? I'll go ahead and stop sharing for a second. So I'll be posting all of these, I'll be posting all of the code on Canvas as soon as we're done here. And then again, for SAS and SPSS users, I'll be posting code to do the same things in those programs, as well as detailed handouts that that kind of annotate the code as you're going through. So you know exactly, it's essentially everything that I said out loud. For R, you'll get in writing for SAS and SPSS. And then I am recording this live lab, so I'll be posting this to Canvas too. But that's all I got. So yeah, so essentially we're done. I'll stick around for a couple minutes if anyone has questions. But other than that, have a good weekend, and I'll see you guys back here on Monday.
Hey, Patrick, I have a quick question.
Sure.
I'm just trying to understand the subset piece. Wouldn't that mean that 69 is just one, like, wouldn't there be an opportunity for there to be outliers in other subsets?
Yeah, correct. Yeah, the only reason why we subset it in this example was just to make it simpler, so that essentially I think, so Leona Aiken was the one who created the example. And I think the reason, it just makes it cleaner, makes the example cleaner. But you're right, if we're looking at all 466, it will likely get way messier.
And we need, I mean, if we're going to use all the data, we need to look at all the data, right?
Yeah, yeah.
Okay, that's the link that I was missing with you using the subset for the example.
Yeah, that's right though. Yeah. So when you're using a data set, you want to look at all of the observations. But for the sake of the example and walking through each of the different diagnostics, we just wanted to work with a smaller sample.
Okay. Is the next homework gonna have us go through this in our own systems? No.
No, I don't think there's going to be anything on diagnostics for homework. That's why Mike had me do the slide lab for this week. I think the next homework is going to be on coding categorical variables. So yeah, there's not going to be a homework dedicated to diagnostics. But if you need to run diagnostics for your own work, you'll have the scripts for R, SAS, and SPSS.
Okay, thanks.
I had a question about the interpretation that we just had at the very end. So would we leave it in the case 69 because the regression is still significant, or would we take it out because that last variable becomes significant?
So it depends. So if the conclusions don't change, then that's probably the easiest case, because you could say whether it's in or not, doesn't matter, the conclusions don't change. When they do change, it's a little bit more tricky. You just have to have a really good reason for why you would take it out. So if you want to remove it, you just have to have a really good reason why. So like, for instance, I think the most obvious reason is, oh, it was a data input error. So like that, if that's the reason and you have evidence to show that, then that's totally fine. But if it's an actual data point, you would have to just have a really good reason for removing it. Otherwise, I think reviewers, or yeah, mostly reviewers, would have a problem with why you took it out.
Thank you.
Yeah. I think another good thing to do is just report both, and then just say that the conclusions change. And you could, that would probably be the best way to do it, is just report the analysis with it and without it, and then just note the difference, and then the difference in results, how in one it is significant and in the other it's not, and then you can give your justifications for why you think, for which model you think would be more valid.
Does that change our alpha level because we're doing another test, one with and one without it?
That's a good question. Probably should be a correction for that, but like Mike said, there isn't a good framework for multiple testing and regression yet.
Mm-hmm.
I think this is stuff that people are still working on. So, but no, I don't think we probably should, but you don't have to. And there isn't a good way of doing it right now. So there's really, yeah, so you probably wouldn't in practice.
Thanks, Patrick. This is really helpful to walk through, so I appreciate it. And in R, you were able to omit the case 69 to run the regression, and it might be in your guides, but in SPSS, is there a way to omit a case, or would we just like delete it from our data set?
Yeah, that would probably be, that'd probably be the most straightforward way to do it, but I'm pretty sure in the materials that I'll post for SPSS, it shows how to do it without.
Okay, thanks.
But yeah, but you could do that as well. So if you'd rather just have one data set with it in and one data set with it out, that's fine too.
Okay, awesome.
Hey, Patrick, great demo. Thanks for this. I wanted to know for sensitivity analysis, is there anything in R that we could use to sort of, once we've identified influential observation, can we run the sensitivity analysis on the other coefficients that were predicted to see if with and without that outlier, how would the coefficients change?
Okay, so for the example, like with and without case 69, how would the coefficients change?
Yeah, like, what I mean by change is, so let's say they were all statistically insignificant with 69.
Mhm.
And let's say removing 69 made them significant, right? So if you were to run into such a situation, like, I think it would be useful to know, like, why did they go from like insignificant to significant, or the other way around? Because that's sort of telling me that, okay, uh, something is on the threshold. Like if you remove something, then suddenly you go from one side to the other.
Yeah, so for this simple case, it's because of case 69. That's the reason why the coefficient for stress went from non-significant to significant.
Right.
Because remember, as we were looking at it, 69 was changing the relationship between those individual relationships of the criterion and each predictor. So in this simple case, you could just conclude that 69 is the reason. If you have more influential observations, then it'll be a little bit trickier. But I think this is enough to conclude that those outliers are influential.
Got it. Okay, cool. Thank you, sir. Have a great weekend.
Okay.